pleasure for me to be here to present this seminar. So I'm going to share the screen. Okay, I think you are seeing the slides, right?
Yes, that's fine.
Okay. So today I'm going to present the composition method in economics, and I will run an empirical exercise in order that you can see how we can apply in practice the composition method, and then I will present some results of my research, my recent research, where I use these methodologies. So the composition method in economics we merged to answer questions such as what are the most relevant factors that explain pay difference between men and women, or between natives and immigrants? What are, for example, the most relevant factors that explain wage inequality increases? And for example, what are the sources of the wage loss of displaced workers? There is an insightful review of the literature published in the Handbook of Labor Economics in 2001 by Fipu and co-authors, which describe in detail this type of methodologies. And the seminal papers by Oshak and Blinder in 1973, which became notorious in labor economics, emerged exactly to explain the aim of understanding the sources of the gender wage gap. And since then, an extensive set of methodological papers aimed at refining and extending the Oshak and Blind decomposition, in particular going beyond the mean and using other statistics of the distribution in order to evaluate it, how the distribution of wages, for example, changes over time, and the changes throughout the distribution in the bottom and the top part of the distribution. So, for example, papers like Freeman that study the changes in the variance of wages, or Machado and Mata that analyze the changes over considering the quantile instead of the mean, are some of the examples. So I'm going to present briefly the intuition behind the seminal papers, the Oshak Blinder decomposition, even though here in this seminar I'm going to focus on the Gelbach decomposition. So as I said, the papers by Oshak and Blinder, the aim was to evaluate the sources of the gender wage gap in order to evaluate which part of the difference could be attributed to difference in the composition, in the characteristics of the two groups, for example, due to difference in human capital, or because the two groups are different in terms of the occupations or the industry where they are employed. And then the remaining part that could not be explained by the different composition of the two groups could be attributed to discrimination. So based on an econometric framework, the idea is, so consider group A and group B. For example, group A could be males and group B could be females. So we estimate, for example, if we want to evaluate the source of the gender wage gap, we estimate using microdata at the individual level a wage equation where the log of wages depend on a set of explanatory variables, XA, and the random error term. A similar equation is estimated for group B. And we know that from the regression model that the raw wage differential between the group A and B, so the difference in the average log of wage for group A and group B could be written in terms of these two components. One, this first term that we call the explained component of wage difference, that gives you how the two groups differ in terms of their observed characteristics. Notice that X bar A and X bar B corresponds to the average of the axes for the two groups. So this gives you what we call the composition effect, and is the part of the row wage gap that is due to difference in characteristics of the two groups. And the second term represents the unexplained component, also called the wage structure effect, and it measures for group B. So in this case, group B is our reference group, the difference of return to characteristics due to membership in this group. So the difference in prices in the returns to characteristics, and corresponds to the unexplained part of the raw wage differential that Blinder and Oshaka attributed to discrimination. So this is the part that is due to difference in characteristics, and this part, the unexplained part, is in general in this framework attributed to discrimination. There is a drawback of the Blinder-Oshaka method, because the proportion explained by discrimination depends on the reference group chosen. So notice that for a given sample, this difference, the difference in the mean of wages is always fixed, so does not change. So is independent of the decomposition. But suppose that instead of using group A as the reference group, we use group B. So in this case, if we use group B as the reference group, so the part that is attributed will be evaluated with the vector of estimates of group B. So the part that is due to composition effects will change. And of course, by default, the part that is attributed to unobserved characteristics will also change. So the Oshaka Blinder decomposition change across depending on the group of reference chosen, even though we can compute considering these two possibilities. But today I'm not going to focus on Oshaka Blinder decomposition, just to give you an overview of the intuition underlying the method. So I'm going to focus on Gelbach decomposition. And so it is very common in empirical research to estimate multiple specifications of a linear regression model to check the sensitivity of our estimates to the inclusion of additional covariates. For example, considering that our parameter of interest, we are particularly interested in the estimate of the coefficient associated with a given variable x1. And so it's very common to estimate several specifications where we have a set of covariates x2 to the base specification, and see if our estimate of the coefficient of interest changes as we have additional covariates to the model. Or simply to account, to be more detailed evaluation, to see in particular how our coefficient of interest, of the variable of interest, x1, changes as one moves from a base specification that has no covariates x2 to the full specification that includes both x1 and x2. And for example, in this paper, John worked with Natasha Fortune and José Varjão, published in the Journal of Population Economics, where our aim was to evaluate the immigrant native wage gap in Portugal using microdata from Quadros Pessoal for the period 2003 to 2008. So we estimate similar wage equations using a sample of more than 7 million male workers and 6 million female workers. And so the idea was to evaluate the gender wage gap and then try to access the sources of this gender wage gap. And so we estimate 3 specifications. So in the first So this variable immigrant is a demi-variable that takes the value 1 if the individual is immigrant and 0 if it is a native worker. And so in the first specification, we only included the demi-variable for immigrant status, year since migration, and a quadratic term in age, and the number of years of schooling, and time and region effects, because this is panel data, so we should account for time effects to account for macroeconomic change in macroeconomic conditions over time, and also control for region effects. And so in this first specification, we observe that wage gap between immigrants on average earn about 28.6% less than native workers. Regarding the female sample, we observe in this specification that women earn on average less 18% than men, holding other factors constant. And then in the second specification, we have a set of controls for employer characteristics, size of the firm, industry, and a variable that we call the concentration of immigrants at workplace. So it corresponds to the number of immigrants in the total number of employees in the firm. And as we have these three covariates, the gap decreases by about 10 percentage points. And then in the third specification, we have job characteristics like the qualification level of the occupation and tenure in the job. And as we have these two additional covariates, so the gap decreases by more around 10 percentage points. So we observe a similar results, qualitative results for the female sample. So we could be tentative to say that, okay, 10 percentage points of the gap between immigrants and native workers is due to firm characteristics, and around 10 percentage points is due to job characteristics. This is not correct, and as pointed out by Gelbach, comparing coefficients estimated from specifications in which covariates are added sequentially to a base model does not generally identify the population parameters of interest, because the order in which we include the variables is not irrelevant unless these additional covariates are not correlated among them. So in a very nice paper published recently in the Journal of Labor Economics, Gelbach proposed a detailed decomposition based on the omitted variable bias formula that allows us to unambiguously disentangle the contribution of each omitted variable for the change in the coefficient of the variable of interest. And so I'm going to present briefly the idea that underlies this method proposed by Gelbach. So considering once again that we are, because it's it's the most common example that we use in labor economics, and I think it's very intuitive. So considering that we are interested in estimating the gender wage gap based on microdata to the individual level, and so we start by estimating the following model. So a model where the log of wages depends on the constant and a demi indicator for gender. So this variable female takes the value 1 for females and 0 otherwise. So we know that if we estimate this model, the estimate of beta 1 corresponds to the difference on the average of the log of wage between the two groups. So it gives you directly the difference in the average wages for between males and females. But probably this is a biased measure of the gender wage gap, as we know that males and females may differ in other characteristics that also affect wage, for example, in terms of education and experience. And so considering that we have these two factors, so considering in just a simple version of the wage equation, similar to a Misery wage equation, where we have the variable education and the variable experience. And so only accidentally we should expect that the coefficient of beta 1 of the gender demi, should coincide with the coefficient of the gender demi in this base model. So these coefficients, these estimated, will be different when we have these two additional covariates. And so our idea is to evaluate how much of the change in the coefficient of the gender demi can be attributed to experience and how much can be attributed to education. So the idea is to try to evaluate how much of this difference in the gender wage gap could be attributed to the variable education and how much could be attributed to experience, the number of years of experience in the labor market. And many often researchers try to solve, make an attempt to solve this problem by estimating an intermediate model where I only include, I have to the base model the variable education, and in this case, I suppress the variable experience. And then based on the estimate of beta 1 in this intermediate model, I could say that the difference between the estimate of the gender dummy in the base model and the estimate of the gender dummy in this intermediate model could be attributed to the variable education, and the difference between these estimates and the estimate of beta 1 in the full model could be attributed to experience. This is not correct, as the order in which covariates are added can affect the counting. So the order, the sequence in which variables are added to the base model are not irrelevant unless we assume that the variable, or we observe that the variable female is orthogonal to education and experience, will the order be irrelevant. Otherwise, the order in which we had the variables to the base model is not irrelevant. And so it is based on this, on the omitted variable bias formula, that Gelbach provides a solution for this problem based on the omitted variable bias formula. And so the Gelbach procedure methodology could be summarized in these 3 steps. So first, we should estimate the model with all the true model. So with all the variables, the specification that we assume that corresponds to the true model, with all the variables. So in this case, with the variable for gender, variable education, and variable experience. And then obtain the estimates of the coefficients of each covariate. Then, in the second step, use the OLES methods to estimate 2 auxiliary regressions of education on female and of experience on female, and then recover these estimates. Notice that these estimates will give you the difference in the average in education, and the average of education and the average of experience between the 2 groups. So we should see how the 2 groups differ in terms of their characteristics, in this case, in terms of average education and average experience. And so we can show that the male-female wage gap that can be attributed to education is given by this expression, and the female wage gap that is attributed to experience is given by this expression. And so Gelbach shows that the change in the coefficient of the gender dummy, when we change from the base to the full model, we can decompose this change in the part that could be attributed to education and the part that could be explained by the experience in the labor market. And so the contribution of each variable is no more than the mean male-female gap in education and experience, scaled by each regressor impact on wages, so given in the full model. So this coefficient, these estimates are given by the full model. So generalizing, and then I'm going to show you a brief empirical application. So suppose this is our true model where we have X1 and X2. So we assume the standard assumptions that error term is not correlated with explanatory variables. So the variables are exogenous. And so we know that under these assumptions, the OLES estimator, which is given by this expression, is consistent. But suppose now that we omit from our model the variable x2. Okay, so suppose that instead of estimating this model, we estimate a model excluding x2. So in this case, the estimator of beta 1, if we exclude x2, will be given by this expression, and we show that the probability limit of beta 1 will be given by this expression. So there is a delta, there is a bias due to the omission of x2. And so it's based on this result, and notice once again that gamma is the matrix of coefficient from projecting the columns of x2 and the columns of x1. So it's based on this result that Gelbach suggests a natural decomposition of the difference between the base and the full model coefficients on x1. So there is a bias from excluding x1 when estimating beta 1, and this bias is non-zero if the expected value of x1 and x2 is different from 0. So it means that if the two variables are correlated, so we should expect a bias from suppressing x1 from the true model. And so the decomposition method proposed by Gelbach is based on this formula. So we can say that the difference between our coefficient of interest, which is the coefficient of the demi variable for gender, this difference corresponds to this decomposition, where here I have the contribution of each variable for this difference. So this part, the gamma corresponds to estimating an auxiliary regression where we run each of the headed covariates on the x1, and this corresponds to the coefficients of the full model. And so we can decompose this change into the sources, to access which covariates matter for this difference. So I'm going to show you empirical exercise, how we can conduct this type of exercise based on a panel data sample. So this is a data that is available in Stata Press. I'm going to use Stata, but there is also you can run these obviously with other softwares. So I'm going to use a sample of individuals, 595 individuals observed over 7 years. So it's a balanced panel. It's data from the panel study of income dynamics from the US. And it's a data set that is available in the webpage of Stata Press. So I'm going to replicate exactly the models that I have been showing you. So a base model where the dependent variable is the log of wages, and the independent is demi for females that takes the value 1 for females and 0 otherwise. And then in the full model, I will have the two covariates, the level of education and the level of experience. So first, so these are the commands to open the data set. I'm going to run. So here I have the data set. So these are the description of the variables. So it's the type of data that we have in labor economics when we want to estimate wage equations. And then I'm going to run the first model by OLES and the base model, and then the full model. And so as you see here in the the base model. So this difference of around 47.4%, it's around because actually the true difference will be the exponential of this coefficient -1. But so we can say that in this sample, approximately, so the row difference in average wages between males and females is about 47.4%. So women on average earn, so considering without condition in any explanatory variable, so it's the raw difference, earn on average less 47.4% than men. Of course, that this gap probably could be underestimated because men and women should differ in other factors, like in the level of education and experience. And then when we have education and experience to our base model, the gap decreases by about 4 percentage points. And so we want to evaluate how much of this difference of around 4 percentage points could be attributed to the inclusion of education and how much could be attributed to the inclusion of experience. And so we should, to apply the Gelbach decomposition, we should run 2 auxiliary regressions, one where we run education on the dummy, the female gender dummy, and then when we run the variable experience on the gender dummy. First, let me show you that. So the first tentative could be to estimate an intermediate model where we exclude education and only include experience. So if I run this intermediate model, I could say that, okay, so here when I include experience, the coefficient decreases from -47 to -45. So I should say, okay, 2 percentage points of this decrease is due to experience and the remaining 2 percentage points is due to education. No, this is wrong, and I'm going to show you that the Gelbach composition will show you that this is wrong, because unless the variables female and education and experience are correlated, so the order in which we include the covariates is relevant. And so applying the Gelbach decomposition, so first I'm going to do this manually, so following all the steps, and then I'm going to show you how you can do the decomposition using the command developed by Gelbach. It's also a Stata command that allows you to perform automatically this decomposition. So the first step is to run these 2 auxiliary regressions of the headed covariates, education and experience on the gender dummy, and then obtain the gamma estimates. And then multiplying these estimates by the coefficients of these variables in the full model, we obtain the contribution of each of these variables to the change in the estimate of the female coefficient. So notice here that the coefficient of the gender dummy changes from -47 to -43. So this is the difference. So this is the difference in the coefficient of the dummy variable when we move from the base to the full model. It's about 3.9 percentage points. And so running these 2 regressions, the auxiliary regressions, so we find here, so we conclude here from this auxiliary regression that females have the average level of education for females is about -0.01. It's very short. It's a short effect, and it's not statistically significant. But when we look for the difference in experience, women on average in this sample have less 3.2 years of experience when compared with males, and this difference is statistical significant. So it seems that in this sample, the two groups are different in terms of their experience level. And so here I will obtain these estimates. So these estimates are the important ones to compute the Gelbach decomposition, and then these estimates of the coefficient of experience and education from the full model. And so based on these coefficients, I can compute the part that is attributed to education of the gap and the part that is attributed to experience. And so here I have the results. So I'm going to show you. So of this difference, and based on these computations, we can say that 3.8 percentage points is due to experience, and well, very close to zero is attributed to education. Why? Because in this sample, the difference in terms of education between the two groups is not very considerable. And instead, so notice that when I use the intermediate model, I could conclude that, okay, of these 4 percentage points, about 2 percentage points is attributed to experience. No, that's not correct, because using the Gelbach decomposition based on the omitted variables formula, we conclude that almost 3.8 percentage points is due to experience, and the remaining negligible value is due to education. So I can obtain these values using the command from Gelbach. So it's the B1X2 command. You can download from the internet. It's not directly available in Stata, but we can download directly from the internet. So you should say which is the dependent variable. The variables that are included in the base model, in this case is only the gender demi variable, and then the variables that we have to obtain the full model. And then the groups that we want to consider in terms of to access the variables that contribute to the difference, to the change in the gender demi when we move from the base to the full model. And here you should indicate which is the variable that corresponds to the coefficient of interest that we are interested in evaluating when changing from the base to the full model. And in this case is the gender demi for female. So if I run this, I have here a detailed decomposition. So here is the total difference when we move from, and the state also reports the estimate of the regression model from the base model, the full model. And so here is the change. And this is the part that is attributed to group 2, which is in this case is experience. And this is the part that is attributed to group 1, which is education. So it coincides exactly with the values that we have obtained when running the auxiliary regressions and then computing based on the Gelbach formula. So now I'm going to show you, so considering now more variables, suppose that we consider more variables. So suppose that my base model, it's a model where the wages depend on the gender demi and time demis. So notice that this is a panel data set. So we have different individuals observing different time periods. So it's common when we have panel data to include time effects, and in this case to account for change in macroeconomic conditions over time. So suppose that this is my base model, and then my full model where I include controls for education, marital status, a quadratic term in experience, because we know that wages are non-linear in labor market experience, a demi variable for unit status, for occupation, a demi variable if the individual is in the manufacturing industry, if it is in a blue collar occupation, and then the time demis. And so we want to evaluate first out the the difference in wages changes as we move from the base model to the full model. And so notice here, so in the base model, the difference is about 47%. When I include all these variables, the difference decreased by 36%. So there is a difference of about 11 percentage points when we move from the base to the full model. And so now I wanted to decompose all these difference could be attributed to each of the covariates that were added from the base to the full model. So how much of this difference is due to difference in education, or difference in union status, or difference in the characteristics of the jobs like occupation, the firm, and so on. So using the Gelbach decomposition, and now I'm going to use the command. So this is the base model, then the variables that the covariates that I had added to the full model, and then the groups. So notice here that in what respects the groups. So I'm not. Okay. So I have included, okay, education, marital status. For example, the variable experience, I include a quadratic term in experience, so it does not make sense to separate the effects of experience from experience square, because when experience changes, the impact on wages will depend on the coefficient of experience, but also experience square. So I can group these two variables in just one group because they correspond to the same variable, and the effect should not be interpreted separately. And suppose, for example, in this case, it does not happen, but in many situations we have a set of dummies for industry or a set of dummies for occupation. In this case, we only have one dummy variable for occupation and industry, but in many situations we have a set of dummies. So you can include all those set of dummies in one group instead of creating a group for each of the dummies for industry, because if you want to evaluate, so considering the variable industry, in many situations, it makes much more sense to include as a group. And so I'm going to apply, and we will evaluate how much of that difference of 11 percentage points could be attributed to each of these covariates that were added from the base to the full model. And so here you have the difference, minus 11 percentage points. And so part of this difference is due to experience, once again, so not experience, marital status. So marital status here, part of this difference. There is also a considerable fraction that we could attribute once again to experience, because the two groups differ in the level of experience. And also in terms of, for example, the union status in this sample. So women are underrepresented, are less likely to belong to a union. And we know that in this case, belonging to a union, we have a premium. And so given that women compared to men in this sample are less represented in unions, so they have a penalty because of that. And also in terms of industry, because manufacturing pays on average higher wages, but women are less represented in manufacturing, and they have a bonus. We could say that they have a bonus here regarding occupation, because so this variable is equal to 1 for those in blue-collar occupations. Those in blue-collar occupations earn lower wages, and in this case, women are less represented in blue-collar occupations, and so they benefit in this case. And so that's why for the variable occupation, we have a bonus. So, and here, so you have a detailed decomposition of this gap that allows you to access the contribution of each of these covariates to explain the gender wage gap and the decrease in this case of the gender wage gap when we move from the base to the full model. So, and that's it that we have done. So in this paper, so notice here we have applied, we evaluated the immigrant native wage gap in the private sector in Portugal. So notice for males that when we change from the base to the full model, there is a decrease of about 20 percentage points. And so we use the Gelbach decomposition to access which are the variables that most contribute for this difference in the immigrant native wage gap. And as we focusing on the male sample of this difference, more than 50% is due to the job characteristics, in the sense that immigrants are employed on average in the bottom part of the hierarchical standing in terms of the qualification level. So they are employed in occupations that correspond to the bottom hierarchical bottom of the level of qualification, and also because they have on average less tenure than natives. There is also part of this gap is also due to the fact that they are employed in firms that employ with a higher concentration of immigrants in the workplace, that has an effect on decreasing wages. And so using the Gelbach decomposition, we can access and can decompose unambiguously and evaluate which of these variables that were added to the base model explain this decrease in the immigrant native wage gap when we move from the base model to the full model. And similar results we obtain for the female sample. I don't know how many minutes I have. Paula, can I?
You used just now 45 minutes, 45. So if you...
Okay, I'm going to be brief.
Yeah.
Okay, so we can extend it with more sophisticated, for using more sophisticated models. So I'm going briefly to show you. So this is a paper, joint work with Pedro Raposo and Pedro Portugal, that will be published, is not published online, but will be published in this summer. So once again, using Quadros Pessoal data. So our aim with this project was to evaluate the sources of the wage losses of displaced workers. So we follow our treatment group is 25 cohorts of workers who lost their jobs in the private sector in Portugal between 1980 and 2014 due to firm closure. And we use a control group, individuals who were employed in firms that did not close in the 1986-2016 period. And so we follow these individuals 10 years before displacement and 10 years after displacement. And we observe with the aim of observing their losses, their wage losses when they in particular after displacement, comparing with their wages before displacement. And the objective was, we find a loss of about 70.2 log points. So meaning that the monthly wages of the displaced workers after displacement were on average 7.2 log points lower than their pre-displacement wages. And so the idea was, to evaluate which are the sources of this penalty that is associated with a displacement event. And our aim was to decompose these losses in terms of the contribution. So it is due to the fact that on the post-displacement period, displaced workers are employed in firms that on average pay lower wage. Is this due to the loss of job title characteristics, occupation-specific human capital, or it is due to the loss, for example, of match quality effects, to the loss of job shopping rents? So in the sense that there is an intrinsic value of each worker firm match. And so we estimated high dimensional fixed effect, where we control for worker fixed effects. So in order to control for observed and unobserved permanent heterogeneity of the individuals, for a job fixed effect and firm fixed effect, and a match quality fixed effect, and with time demis. And so we include demi variables. These demi variables, dk, take the value 1 10 years before displacement, 0 otherwise. D minus 9 takes the value 1 9 years before displacement, 0 otherwise. D0 corresponds to the displacement year, D1 to 1 year after displacement, 3, and so on. So this is the OLES estimate, even though our baseline model is a model that controls for worker fixed effect in order to account for difference in unobserved characteristics of the individuals. And so we notice that, but looking at the OLES estimates as after the displacement, so this gives you directly the difference between the displaced and the non-displaced. So the difference increases when we account for worker fixed effects. So this is the within difference in wages. So here we have the evolution of wages, of worker wages. And so we observe that after displacement, this difference is negative. And so 10 years after displacement, the difference, and comparing with the 0, the baseline here, is about 7.2 log points lower than in the baseline here. And so we added to this base model a firm fixed effect, a job title fixed effect, and the match quality fixed effect that corresponds to the full model, in order to evaluate how much of this difference of 7.2 log points could be attributed to firm fixed effects. And so here we have the net difference between the pre-displacement period and the post-displacement period. And so I focus on the bottom line. And so of these 7.2 log points, 2.2 is due to firm fixed effect, 2.3 to the loss of match quality fixed effects, and 2.3 to the loss of job title fixed effects. And so we conclude that sorting into lower paying job titles represents a large component of the monthly wage loss of displaced workers, accounting for 37% of the total average loss. Firm and match fixed effects account respectively for 31 and 32% of the total monthly wage loss. And so we can apply these. So these examples are based on labor economics, but you can apply to in other fields, for example, to evaluate the source of the difference in test scores between schools, or in terms of rankings of school. I have also applied, not this particular method, but a composition method in this, with the same rationale, for to evaluate the difference in survival probabilities between pushed spin-offs and pull spin-offs, and try to evaluate which is the role of human capital in explaining the survival of new startups, distinguish between pulled and pushed spin-off. So my demi variable was equal to 1 for a pull spin-off and 0 otherwise. So you can apply this kind of methodologies to different in different fields, and with in many different issues and problems. And so briefly, so that's it, what I would like to share with you today. Thank you for your attention.